Hello everybody, welcome to today's video. Today we're going to be covering the unit circle. So we'll start off by looking at the definition of the unit circle and then look at the definition of all 6 trig functions using the unit circle. Then we'll look at the Pythagorean identity to help solve problems. As you might imagine, that is very closely related to the Pythagorean theorem. Then we'll find sines and cosines, kind of our big 2 main trig functions, although there are 4 more that we will look at more closely as we move forward. But at these big kind of main angles here, pi over 6, pi over 4, pi over 3. Then we'll look at the domain and the range for the sine and the cosine function. We'll talk about the domains and range of the other 4 trig functions in a future video. And then we will use the reference angles. So we talked about reference angles in a previous video to find common values on the entire unit circle. So we'll be able to kind of fill the whole thing in for these common values. So first we will look at just the definition of the unit circle. So as you might imagine, the unit circle is a circle. It has a radius of 1 unit, which is why it's called the unit circle. So if we look at the radius right here, it wasn't my best line, but this radius right here is a unit of 1, whatever we want it to be. Feet, meters, centimeters, who cares? It's just going to be 1 unit for right now. And it's centered at the origin of the coordinate system here so that we can talk about things in a nice way. But the unit circle consists of all xy points that satisfy the equation x squared plus y squared equals 1. So you might be familiar that the equation for just a circle in general is x squared plus y squared is equal to the radius squared. Here our radius is just 1, and 1 squared is just 1, so that simplifies to just 1. So what we're saying here is that any of the points that lie on this circle satisfy this equation. So circles are just all of the points that satisfy this equation. So let's go back and we will, I don't know why I put all those dots there as I went, now I have to undo them all. But what we want to do here in this example is show that this point negative 1/4 square root of 15 over 4 lies somewhere on this unit circle. So that's what we're going to do. What we need to do is just plug these into the formula that we have above and show that we get 1. So if I take x, which is negative 1/4, and I square that, and I add to that y, which is positive 15 over 4, also being squared, what I should get is 1. And if I do, then this point lies on the unit circle. So if I square that left-hand side, 1/4 squared will give me positive 1/16. So square the numerator, we still get 1. Square the denominator, we get 4. We square 4 and we get 16. And then that negative becomes positive. And we can square the right-hand side too. If we do the square root of 15 being squared, we just get 15. Square the denominator, we also get 16. So of course this says 16 over 16, which is just 1, which is what we were hoping to see. We were hoping to see that if we squared x and we squared y, that we would get 1, and we do. So we could go plot this over here if we wanted to, since we know that this is about 1/2. So I mean, I guess I could go in and plot some points that we do know as well. This is 1, 0. The one up here is going to be 0, positive 1. This point over here is going to be negative 1, 0. And then this point down here is going to be 0, negative 1. So we are trying to plot this point, negative 1/4. So I'm starting in the negative direction. There's negative 1/2, so negative 1/4 must be right around there. And then if I kind of plot that up here and map it over, then this right here must be the square root of 15 over 4, which makes a lot of sense. That's dangerously close to 1. If we had the square root of 16 over 4, that would be 1. So it makes sense that it lives real close to the top there. So there's our point, negative 1/4. Square root of 15 over 4. So going forward, we will see that if things live on the unit circle, which they should, they will satisfy this equation, which will be a huge tool that we will use to help solve some problems here. So now that we have the unit circle, we will define the 6 trig functions using the unit circle. So you might notice just in this picture here that there isn't any angle that's being listed, and that's because we're not defining these trig functions by an angle, at least not quite yet. Right now we're defining it by looking at some arc length t going along the unit circle here. So we're going to let xy, this point P at the coordinates xy, be a point associated with a real number t that is measured along the circumference of the unit circle, starting always at 1, 0. So we're always starting kind of at the spot, maybe it makes the most sense, the spot that we normally start at. This is where we have our initial angle for a standard angle, or initial side for a standard angle. And the way that we define things now is that the x value is called the cosine of t, and the y value of this point is called the sine of t. And t, again, is this measurement along the circumference here, this arc length here. We can start filling in some things that we just said over here, that the sine of t is just y, and the cosine of t is just x. It is maybe as straightforward as that. That the cosine value is associated with the x-axis, and the sine value is associated with the y-axis here. To get the tangent, we will, if you think back to what we talked about with right triangle trig, we looked at that being the opposite over the adjacent, so you might not be surprised here to find that we're going to get a ratio of things that we already know, which is y over x. And x wouldn't be able to be equal to 0 in this case. If it was, we divide by 0, and that would be bad. So later on, when we talk about the domains and ranges of these functions, we will see that x being 0 would not work for our tangent function. So we'll make some sense of that domain in a future video. The cosecant is what we have next, which we know from previous videos that that's 1 over the sine, so we're maybe not too surprised to see that that's 1 over y here, since the sine is y, the sine of t. And here y wouldn't be able to be equal to 0, because if it was, then we divide by 0, and that's no good. So the secant we know is 1 over the cosine, so writing 1 over x here hopefully makes some sense. And of course, x wouldn't be able to be equal to 0. If it was, we divide by 0. And then the cotangent is going to be the reciprocal of the tangent. So here we'll have x over y, and y can't be equal to 0. So here we have the 6 trig functions defined using the unit circle. Again, we haven't talked about an angle yet. We're just talking about traveling some distance around the circumference to some point. So there's a point associated with this value of t that we're traveling around. The x value there is the cosine of t, the y value there is the sine of t. We get the other 4 by just piecing them together in ways that we are somewhat familiar with. So here we have an example. We want to evaluate all 6 trig functions at t corresponding to the given point. So here we've traveled through the first quadrant, through the second quadrant, and now we're down on the third quadrant. At this point, negative 2/3, negative square root of 5 over 3. We could verify that this is on the unit circle by squaring both and then adding them together, and we would see that we would get 1. But we don't need to do that here. We'll just trust that it does live on the unit circle. But I know that the sine of t, if I want the sine of t, that is just the y value that's here. So it is as simple and as straightforward as just writing in negative square root of 5 over 3. And the cosine value is just the x value over here. So we can just write in that the cosine of t is negative 2/3. Now that we have these two, we can just use those relationships that we saw on the previous page to get all of the rest of them here. So the tangent of t, maybe it will be a little bit helpful to write in just as reminders that the sine of t is equal to y, and the cosine of t is equal to x, just so that as I'm filling things in here, and I remind you that the tangent of t is y over x, that we can quickly see which one was y and which one was x from above. So if I want to do y over x here, I'm going to do negative square root of 5 over 3 divided by x, which is the negative 2/3. You put an equal sign in between there. So now we can just start simplifying. So we'll have square root of 5 over 3 times, and we'll take the reciprocal, negative 3 over 2. Now we see that the 3's cancel, those negatives cancel, and we're left with the square root of 5 over 2. So here we've got the tangent of t being the square root of 5 over 2. If I want to find the cosecant of t, well, that is going to be 1 over the y value, 1 over sine, and sine is equal to y. So here, if I want to simplify, we're going to get 1 over, I know that y is negative square root of 5 over 3. If I just use some reciprocals here, I'm going to get negative 3 over the square root of 5. And now I'm going to want to rationalize my denominator. This is a fine answer. There is sometimes good reasons to rationalize denominators. so we're just going to do it because it's good practice. So square root of 5 over the square root of 5 just says 1. I'm multiplying by just some funky form of 1. I'm not changing the value of anything. I'm just changing the way that things look. But this is nice because the square root of 5 times the square root of 5 is just 5. And in the numerator, we'll have negative 3 times the square root of 5. So here is my cosecant of t. I suppose I could have just gotten that kind of straight from the sine of t by knowing it's the reciprocal and just taking this reciprocal straight away and then rationalizing the denominator, but this works as well. Same thing with secant of t. We know that this is 1 over x from the definition, so we're going to get 1 over negative 2/3. Again, we can take the reciprocal of the denominator and we will get negative 3/2. So that one falls into our lap fairly straightforward there. And then for the last one here, we need to get the cotangent of t. So the cotangent is just going to be the tangent flipped upside down. Well, I guess we should maybe write it the way that we did before, and that's going to be x over y. We could also just look at taking the reciprocal of the tangent, but let's go through the full details here. So x is negative 2/3, and y is negative square root of 5 over 3. If I multiply by the reciprocal of the denominator, I'm going to have negative 2/3 times negative 3 over the square root of 5. The 3's cancel, the negatives cancel, and now we've got 2 over the square root of 5. We'll rationalize our denominator there, squeezing that in, and we will get 2 square roots of 5 all over 5. So there is our cotangent. Again, we could have just looked at our tangent and taken a reciprocal there, rationalized the denominators, and gotten it that way too. But I wanted to go through the full definition there. So, all right, we've got all 6 trig functions at t, just using the definitions here. So now we are going to relate what we have defined for these trig functions and relate it back to an angle. So since we are using the unit circle, now we're remembering that we're using the unit circle, and that means that our radius here is just equal to 1. So if theta is just some central angle here with a terminating side passing through P, so now we're talking about this angle passing through this point P, that's still associated with T, but now this angle and T have something related here. Then from our arc length formula that we saw before, we just get that T is equal to theta, and this is the punchline here. So what we've got, if I kind of maybe separate out what we have here, this here is just our arc length formula, that the T, the arc length here, is just equal to the radius, which is just 1, so the radius is 1, times theta in radians, which we've got here, so we just end up with T being equal to theta, which is nice. So now instead of thinking about just this arc length, just this distance being traveled around the circumference, because the radius is just 1, we can relate that back and know that the theta value is the same as T. So we can make this just kind of quick change over here, since we know that T is equal to theta. Instead of talking about the sine of T, which is still that arc length distance, we can now talk about the sine of theta, which is the angle associated with T. So this is just kind of formalizing things for us so that we can use the unit circle, relate it back to this point, this xy point, and be able to start taking these trig functions at a specific angle associated with this distance T and this point P. All right, so next we're going to take a look at the Pythagorean identity here. So recall that the equation for the unit circle is x squared plus y squared equals 1. Since we now know that x is equal to the cosine of t and y is equal to the sine of t, we get the following identity, that the cosine squared t is equal to the sine squared t. So we're just literally making this substitution here where x squared plus y squared is equal to 1. Well, we know that x is equal to the cosine of t, so this is being squared. And we know that y is the sine of t, which is being squared. And this should equal to 1. And then just changing kind of how we notate cosines being squared and sines being squared, we get, as promised, what we have above here. So this is just, and hopefully you recognize this as just being the Pythagorean theorem. And this is why we get this as the unit circle definition, that we have x here as one of our legs and we have y here as the other one of our legs. Trying to make that not so sketchy looking. And if we square the legs, we should get the square of the hypotenuse, which is going to be 1, and you square that and you still get 1. So hopefully this is making a lot of sense. We're going to be using this idea going forward a bunch, whether we're talking about sines and cosines or x's and y's. We know that we can use the Pythagorean theorem by dropping in these right angles, these right triangles rather, and getting what we want. So here we are going to do an example, and we're going to say if sine of t is equal to 3/7 and t terminates in the second quadrant, we want to find the cosine of t. So what this is saying is, here's some distance t, and we're going to travel around the unit circle here, and it's terminating in quadrant 2. Now I don't know that it's exactly right there. In fact, it's probably not, but I'm just kind of putting it somewhere in the middle, and then we can go and figure out what's going on here. And maybe not change our picture. We'll just say our picture's not drawn to scale. But this is the idea here. So here's our arc length t, and it's going to be associated now with this angle theta. So theta is the same as t because the radius here is just equal to 1. But what we can do is we can drop in this right triangle, just like we saw in that previous slide. And we can take a look now at this reference angle theta prime here. So we're going to get a little bit more formal with using these reference angles going forward. But what we're looking at here is that the sine of t, which is the y value, so we've got an x value here, which is giving us this distance, and we have an associated y value, which is, oops, I didn't change color like I wanted to, which corresponds to this side over here. And we know that the sine of t, which is equal to y, is equal to 3/7. So we know that this side isn't just y, but it is 3/7. And we're asked to find the cosine of t, which is the x value. So we're asked to find x, asked to find cosine of t, which is this x value. So if I can figure out this x value, we should be good to go. So using the Pythagorean identity that we saw on the previous page, we know that the cosine squared of t should be, plus the sine squared of t should be equal to 1. We don't know what the cosine is, but we do know that the sine, I keep writing equals instead of plus, we do know that the sine is 3/7, and we're going to want to square that as well, and this should be equal to 1. Now we can solve for cosine. We can just treat it like a variable, just like as if it was x or something, but we'll just keep it as cosine. So we've got cosine squared of t is plus, what's this going to be? 9/49 is equal to 1. I can subtract 9/49 from both sides, and we'll have cosine squared of t is equal to 1. I'm going to rewrite 1 as 49/49 minus 9/49, so that we just get 40/49. So just doing some quick rearranging there. So at this point, I've got that the cosine squared of t is equal to 40/49. Now we will take the square root of both sides. When we take the square root of both sides, we need to include a plus minus, because there are, once you square something, it doesn't matter if it's positive or negative, it always ends up being positive. So we need to keep that condition in there. So now that we've got the cosine t is equal to plus or minus, if I think about simplifying this a little bit, I'm going to get that this is the square root of 40 over the square root of 49. If I rationalize the numerator, I'm going to get 2 square roots of 10 over 7. So here I've got the cosine of t is equal to plus or minus 2 square roots of 10 over 7. So notice that there's 2 solutions here that we need to consider, and sometimes we get extraneous solutions. So that's what we need to consider. Notice that because we are in the second quadrant, that means that the cosine value needs to be negative, because everything in this direction that lives on this x axis is going to be negative, which tells us that we are going to throw out throw out the positive case and we will just have negative 2 square root of 10 over 7. So if I want to now write in what my cosine of t is, we have found it. This is the negative 2 square root of 10 over 7, being our cosine value, and then our sine value was given to us is 3/7. So there we go. We have found the cosine of t. I don't have it explicitly written here, but I could maybe just write it in here, is equal to negative 2 square roots of 10 over 7, or over 7, sorry. And I've plotted it here as well so we can see. So obviously not in exactly the right spot. I'm sure if you plotted this, it's going to be somewhere a little different. But we can just use this picture to kind of rough things in, drop in these right triangles, and be able to solve from there. All right, we're going to do another example, but we're going to treat it a little bit different. So we could do this the exact same way. This one, we have the cosine of t being 24 over 25, and t terminates in the fourth quadrant. So we could think, okay, we're going to travel around to the fourth quadrant here. We're going to have some terminating point t. We're going to do this, and I could still, do like I did, drop this in. Now I know that the cosine of t is going to be 24 over 25. This is 1. This is not y, but maybe the sine of t. And then I could go set that up just like I did before and solve. But I want to think about this a little bit different. You might notice that I didn't label any of the kind of standard endpoints here as being 1, 0, or 0, 1, or negative 1, 0, or 0, negative 1, because I don't want this to be unit circle. I just want this to be a circle, maybe a unit circle that's just been stretched out or shrunk to do what I want here. So we're going to just use things that we know from the previous video on right triangle trig to do this. But we're going to kind of do the same thing here. So we're still thinking about traveling around this not unit circle, but just circle in general, and finding, whatever point this terminates here in the fourth quadrant. And we're still just going to drop in an angle and drop in a right triangle just like we did before. But now, instead of thinking about this being a unit circle, we're just going to use the fact that we know that the cosine of theta is equal to the adjacent side over the hypotenuse. So again, just referencing back to things we know from right triangle trig. And we know in this case that this should be 24 over 25. So instead of making this a unit circle, it's been stretched out by a factor of 25. I know the hypotenuse is 25, so I can write that in there. And I know that the adjacent side, here's our still kind of our reference angle. Maybe I'll call it t prime or something. I don't really want to talk about thetas. There's a little loosey-goosiness in here a little bit. But I know that this adjacent side is going to be 24. So now I just need to find whatever this y side is, the opposite side here. And we can use it still just using the Pythagorean theorem. So I know that y squared plus 24 squared should be equal to 25 squared. So y is going to be, or y squared is going to be equal to 25 squared is 625 minus 24 squared, which is, I have it written down somewhere, I did this earlier, 576, which says that y squared is equal to 49, which says that y is equal to plus or minus 7. So again, we have two proposed solutions. We need to see which one is the actual solution here. Remember that since we're in the fourth quadrant, all of these values here are negative. All of these y values are going to be negative. So here we're going to get negative 7 as the y value. So this tells us that this side here is going to be negative 7. But this doesn't answer the question quite yet. The previous one, this gave us the solution, but now we need to put things back together. And remember that the sine of t is going to be the opposite side over the hypotenuse. And now we know the opposite side is negative 7. The hypotenuse is 25. So here is our sine of t. It is negative 7 over 25. So what we did in this example was not use a unit circle, but we still used a circle. Like I said, even in the previous video, I said that we will be using circles just kind of as references. Maybe not exactly the unit circle, but we are still using a circle here and using things that we know about the unit circle to kind of drop in these right triangles and then use things that we know from right triangle trig to solve this one. So wanted to show you both these problems are asking us to do the same thing. Here we're just straight up using the unit circle definition. Here we're using not a unit circle, but a stretched out unit circle, and then things from right triangle trig to solve. So either way, totally works. Pick your poison and go from there. All right, now we're going to start looking at finding common values on the unit circle here. So our common values are pi over 4. This will be this one here, and the next one we'll look at is pi over 3 and pi over 6. So you might remember some stuff from when we talked about this before, and know some relationships here. So we're actually going to find our relationships here a couple different ways. The first way here is just kind of geometric a little bit, and then we'll use things that we might remember from before. So what we're told here is that this angle down here is pi over 4. Since we know two of the angles, 90 degrees and pi over 4, or pi over 2 and pi over 4, that just means that this other angle here also has to be pi over 4, which tells us that this is an isosceles triangle. If two of the base angles are the same, then we have an isosceles triangle. So, since this point here, we're trying to figure out the sines and the cosines for this value here. So maybe I should have said that up front. We're trying to find sine of pi over 4 and cosine of pi over 4. Whatever this xy point is will tell us whatever the sine and the cosine is. So let's think about this here. We know that this value here is going to be x, and we know that this distance here is going to be y. But since this is an isosceles triangle, we know that the side lengths are the same, so y is equal to x in this case. So both side lengths of this isosceles triangle are the same length. So instead of writing x squared plus y squared equals 1, I can write x squared plus x squared equals 1, since I know that y is equal to x. So this says 2x squared is equal to 1. If I divide both sides by 2, I'll get that x squared is equal to 1/2. And if I take the square root of both sides, I will get that x is equal to plus or minus 1 over the square root of 2. Since we're in the first quadrant here, everything is positive. X values are positive, y values are positive, which means that we'll be looking at the positive 1 over the square root of 2, and we'll rationalize our denominator. So let me again just say that, like, this is a fine answer for me. We don't always need to rationalize denominators. You won't always see them rationalized, but just know that this is the same as, rationalizing the denominator, which is multiplying by the square root of 2 over the square root of 2. This is just some funky form of 1. It's not going to change the value of anything. It's just going to change the way that things look, and we're going to get the square root of 2 over 2. So either one of these is perfectly fine here. So we've got the x value now being the square root of 2 over 2, but we know that this is also the same as the y value. Because x is equal to y, we get that y is also the square root of 2 over 2. So square root of 2 over 2. So now we have the sine and the cosine value. The cosine of pi over 4 is the square root of 2 over 2, and the sine for pi over 4 is also the square root of 2 over 2. So what's kind of nice about those is they're the same. We don't need to really think about. Now as we start maybe moving around the unit circle and finding related reference angles here, we might start having to think about the signs on these. They won't always be positive square root of 2 over 2, but we might start thinking about where they're negative as we go forward. I want to think about this one just a different way here, using things that we have seen in a previous video. We still know that this is pi over 4 here. So you might remember that if we have a 45-45, or pi over 4, 90, pi over 2 triangle, and we call this side S, which means that that side is also S. We still have an isosceles triangle. We saw that that meant that this hypotenuse side was going to be S times the square root of 2. So this is just using some relationships that we've seen before in a previous video. What I want to do now is scale this triangle down. Maybe I could even, well, we'll leave it like it is. But I'm going to scale this triangle down by dividing all the sides by a factor of the square root of 2. So now I'm getting this smaller triangle. I'm maybe not necessarily going to draw it much smaller, but I'm getting this smaller triangle that's been scaled down, and now I know that, well, these are going to cancel, and I'm just going to have s as being this side, and this is going to be s over the square root of 2, and this is also going to be s over the square root of 2. Now what we could do, since we are trying to look at things on the unit circle here, notice that the hypotenuse of this triangle is 1. So what we're going to do is let s equal 1, and now if I draw the triangle that we had before, I know that s is equal to 1, which means that this side length is 1 over the square root of 2, and this side length is 1 over the square root of 2, which we saw before is the same as square root of 2 over the square root of 2, rationalizing the denominators there. So we get the same relationship both ways. We can either use this geometric proof here, using that those side lengths must be the same, and just using the Pythagorean theorem to figure out the side lengths here, or we can use the relationships that we already knew. Now, honestly, these are being proven the exact same way, but here we're just using that relationship that we already saw from before to show that the cosine, this length here, is going to be the square root of 2 over 2, and that the sine, this distance here, is also the square root of 2 over 2. So we get this point here being the square root of 2 over 2 for the cosine, and square root of 2 over 2 for the sine. So there we go, just a couple of different ways to show the same thing, but now we know the sine and the cosine at pi over 4. All right, next we will take a look at finding these common angles now at pi over 6 and pi over 3. So we're going to do a similar geometric argument as the one that we just did for the 45, 45, 90, or the pi over 4, pi over 4, pi over 2, however you want to think about that. But here we have our angle at pi over 6, so we're dropping in our right triangle here. Since we know two of the angles, pi over 2 and pi over 6, that just tells us that this last angle here has to be pi over 3. We need them to all add together to be pi. So what I'm going to do is just take the triangle that we have here and kind of blow it up to the side. Look at a little bit bigger version of it here, and we're going to kind of do a similar argument that we did with those s's before. So we know that this side down here is pi over 6. That's our smallest angle, which tells us that this is our shortest side. We know that the hypotenuse is then double the shortest side, so this is stuff that we saw in a previous video. And since this is the pi over 3 side, then that tells us that this side length is s times the square root of 3. So again, I'm just using relationships that we saw in a previous video. You can check that out if you want to see why all these things are true. So I'm going to do like I did last time and scale this down, but now I'm going to divide everything not by the square root of 2, but just by 2, because I'm trying to get my hypotenuse to just be 1. I'm trying to get this into the unit circle. So I'm dividing everything by 2. I'm scaling this down by a factor of 2, so now I've got this smaller triangle here, and now the hypotenuse is just going to be s. This shorter leg is going to be s over 2, and the longer leg is going to be s times the square root of 3 over 2. And just like we did before, we will let s be equal to 1, because I'm trying to get my hypotenuse to just be 1. So once I do that, I'll get this triangle sketched back in here. Come on. Now I know the hypotenuse is just 1. I know that the short side is going to be 1 over 2, and I know that the longer side is going to be the square root of 3 over 2. So now I have the sine being 1/2 and the cosine being the square root of 3 over 2. So that tells me that this point, if I wanted to write this all in super explicitly, is square root of 3 over 2, 1/2. That is this point right here, or I could write explicitly somewhere else that the cosine of pi over 6 is equal to the square root of 3 over 2, and the sine of pi over 6 is equal to 1/2. Well, let's talk about pi over 3 as well, and we're going to use the exact same triangle. So don't forget that we can look at this angle here, so this being an angle of pi over 3, and we get a similar right triangle. So it is going to be this guy here. Now, if our bottom angle here is pi over 3, then that means that this one is pi over 6, which means that we have the same triangle that's just been transposed and maybe even reflected here, but we have the same relationships. I wrote pi over 2 at the top there. That should say pi over 6. But same story. We can reflect this and we get the same thing that we see now, that the sine of pi over 6 is now the square root of 3 over 2. If you think about kind of mapping this over, that's much closer to 1 than it is to 1/2, so that's square root of 3 over 2. And then mapping it down here, we see that the cosine of pi over 6 is equal to 1/2. So they are switching roles here. And we saw that again in the previous video, these kind of like co-function identities where the cosine of one angle is equal to the sine of its complement angle. So we're seeing that here again. So now we've got kind of these big main angles here. I believe on the next slide we'll see them all in one place. In kind of a nicer, cleaner version than I was able to draw. So we see at 30 degrees, or pi over 6, we've got that the cosine is square root of 3 over 2, and the sine is 1/2. We see at 45 degrees here, or pi over 4, square root of 2, square root of 2, square root of 2 over 2, and square root of 2 over 2, which is what we saw on the previous slides. And then for 60 degrees, or pi over 3, we get that the cosine is 1/2 and that the sine is square root of 3 over 2. We're also seeing some of the other common ones here. So 0 is the point 1, 0. So don't forget that this says that the cosine of 0 degrees is equal to 1, and the sine of 0 degrees is equal to 0. So just using that point there, and same thing with this point up here at 90 degrees, or pi over 2. This says that the cosine of 90 degrees is equal to 0, and the sine of 90 degrees is equal to 1. So we can still just use those points there. I don't know if I've set those explicitly, but those are important to notice as well. So there we go. This gives us some nice things to not necessarily memorize, but I think as you work through these, they will sort of get memorized. Or there are some kind of nice ways that I've alluded to already to kind of figure out what these points should be. But there we go. We've got our common values here for pi over 6, pi over 4, and pi over 3. All right, so now I want to take a minute and talk about the domain and the range for the sine and cosine functions. We'll talk about the other 4 in a future video, but let's just kind of think intuitively here a little bit through this. So we want to look for the domain, for the sine and cosine functions. Oops, I don't want to write the whole thing out. We'll just write cos theta. So let's just think about this. Remember that theta is an angle. So we're thinking about starting from 1, 0 and traveling, we're traveling some distance t, but this is related to some angle theta that's also being traveled around here. But let's just think about what we can plug in. So as we're thinking about plugging in values, here are all the, maybe we'll think in degrees, all the degrees from 0 to 90, those are all okay. And then 180, that's okay to plug in. And then everything there to 270, that's okay. And then everything up to 360, and that's okay. So nothing wrong with anything so far, but we can just keep going, right? Like we keep going all the way around here, get up to 720, and then keep going all the way around here, and yada, yada, yada. So we can just put in anything from 0 to positive infinity, it looks like, are all okay to plug into the sine function here. But there was nothing special about what we just did. We were going in the positive direction, but we could have just as easily started going in the negative direction where we have negative 90 degrees, and we could plug in all of those values and find solutions, and we could just keep going. And same story, we could just keep traveling in the negative direction as many revolutions as we want. So we see that anything in the negative direction also works here. So the domain for both the sine and the cosine function here, let me get rid of my scribbles, is negative infinity to positive infinity. So there are no restrictions to the domain here. You're allowed to plug in anything you want, and we should get an output. We might see in the future when we talk about the other four that they do have some restrictions on their domains, but sine and cosine do not. All right, now we will take a look at the range for sine and cosine. And we're just going to focus maybe on one at a time here, but we'll take a look at the sine. We could take a look at either one, it doesn't really matter. But let's take a look at the sine, and we'll start just at 0. So I wrote theta, but I want to start the sine of 0, which is right over here. So the sine of 0 is just equal to 0, or it's just the y value here. So okay, we know that 0 is in the range, so can we put in positive values? Can we put in negative values? So let's just think about starting to travel in this direction around here until we get up to pi over 2. So I'm doing things in radians now, I guess. But we get up here to pi over 2, and we see that the sine value is now 1. So we're at least getting up to 1, but we can also see that this is where it maxes out. It's not going to get any higher than 1, because then it starts to turn around as the angle increases and come back down to -1. So the sine of pi here is equal to -1. I'm sorry, a 0. We're back at 0. I was looking at the cosine, not the sine. Sine of pi is equal to 0. We're back down to 0. We will get -1, I promise. In fact, it's going to happen right now, because as the values continue to get bigger, now we've hit down here at -1. So the sine of 3 pi over 2 is equal to -1. So here we can see the sine value being -1 down there. But same story as the positive one. It's not going to get any lower than that. That is literally the lowest point on the graph before it turns around and starts heading back up to 360, or to 2 pi here, since I'm doing things in radians. So sine of 2 pi is back to 0. So we can see here, kind of looking at the extremes and the intermediate values here as it travels around, that the domain, or I'm sorry, the range is going to be from -1 to +1. And hopefully you can see that on the graph here. As the outputs, we're starting at 0, they grow to 1, and then they turn around and head back to 0, and then they go all the way down to -1, and then they turn around and go back to 0. So they just kind of bounce back and forth between -1 and 1. And the same thing is happening for the cosine as well. So I won't write all of these out here, but we can still take a look at what's happening if we're thinking about the cosine. Here we could start with 1 at 0 degrees. So the largest that the cosine will ever be is 1 degree, or I'm sorry, not 1 degree, but a value of 1. And then as the angle starts to move, now we have an output of 0. So it's gotten smaller, and it continues to get smaller until the cosine becomes -1. And then it starts to grow again until the cosine becomes 0, and then the cosine returns back again to +1. So same story, we get that the range for the cosine is also from -1 to +1. All right, now we're going to use some reference angles to try and find some values here for we're not going to start looking at finding values right now. We're just going to talk about the reference angles. Then we'll go start using these reference angles to find some values for sine and cosine. So the first thing we're going to do here is just find these reference angles. So we're going to start with 225 degrees. It's maybe the least tricky of them here, and hopefully most tangible. So we're looking for 225 degrees, and we want to find the reference angle. So I should maybe even go back and say that if theta is equal to 225 degrees, we want to find theta prime, which is the reference angle. So let's just sketch that in here. I'm thinking about traveling around 225 degrees, so there's 90, there's 180, and if I go another 45 degrees, then we hit this point right here, which is associated with this angle. So there we go. There's 225 degrees. Now I think sometimes it's kind of visually, it's easy to see visually what the reference angle should be. If we're looking for our reference angle here, it's going to be this little distance right here. We're always mapping back to the x-axis or the horizontal axis to find our reference angle. So let's think about how we could find that. I think that it's not too off base to think that we already know that that's 45 degrees, since I already said that out loud. But let's use kind of what I said to draw this to get exactly what we want here. So let me choose some colors. What we're doing here is we're first starting to travel around this unit circle, and we go past the horizontal axis until we get to where we are, which is at 225 degrees, which was too far. We traveled 225 degrees, which was too far. What we're going to want to do now is subtract off by how much farther we went than we were supposed to. So now if I'm traveling around with the pink, we're supposed to stop right here. So I'm going to want to subtract off that distance of 180 degrees, which should just give me the middle part left over. So if you take a look, I did the green, which was all the way around to 225, and I'm going to subtract off the purple, which was only 180, and we'll get that this is 45 degrees. So here is our reference angle, theta prime, which is 45 degrees. So as we move forward, we can just use the fact that we know sines and cosines at 45 degrees, think about what quadrant we're in, and change the signs, and we should have some answers here. Let's take a look at the next example here, which is finding the reference angle for 701 degrees. So we want to find theta prime. Let me clear off our little circle here, but we're going to do the same type of thing. Well, actually, before we do this, notice that 701 is a pretty large angle. It means that we're going to have to go at least one revolution here. So the first thing that we're going to do here is just find the coterminal angle in the interval from 0 degrees to 360 degrees, because then we don't have to think about doing all these revolutions. We can just use this, and this will help make the subtraction a little bit nicer here. So if I do 701 degrees minus 360 degrees, which is one full revolution, and again, to find coterminal angles, I'm just going to start subtracting off full revolutions until I find an angle that's in our interval here from 0 to 360. So I think when I do this, I get that this is 341 degrees, which is in our interval. So 341 degrees will be our coterminal angle, and then I can find where that is. So that's going to be coming around here, 90, 180, there's 270. So we're going to get kind of a lot of the way towards 360, but we'll say 341 is right around there. Here's our angle that I can drop in, but here is what we're looking at, which is 341 degrees. So again, what we're trying to find is this angle here. So this is our theta prime. So again, I want to think about, okay, how can I find this? If I travel a full revolution here, that would be too far. So I'm always thinking about traveling too far to the horizontal axis or to wherever I need to be. So I'm traveling all the way around here using the green until we get back to where we started from. So we've got 360 degrees, but that was too far. We traveled too far. What we want to do is subtract off the difference. So we're traveling all the way around here, now only just to the angle that we're going to, which is 341 degrees. And what we get is the difference, is this area here that is left over. So I'm doing the full green, which was too far. I'm subtracting off the pink, which is where we're trying to go, and that difference is the distance to the horizontal axis, which in this case is just going to be 19 degrees. So this is theta prime for our original, which was 701 degrees, but we found a coterminal angle so we could sketch it in, and then we used that to get our reference angle. All right, the last one here is in terms of radians. This one is for 5 pi over 3, so I'm going to just move some of my work up here a little bit to give myself some space, and then I will erase all of the junk from the last one off of our template here. And now we will take a look at, I guess, I'm not labeling things very properly here. I guess this was one part A and B. Maybe I should change that. We'll call this part A, and we'll call this part B. All right, so now we'll do number 2, which is going to be an angle of 5 pi over 3, and we want to find theta prime. Theta prime. Okay, so let's sketch in where 5 pi over 3 is. This is within just one revolution, so we don't need to find a coterminal angle first. But if I have to find 5 pi over 3, I just start counting pi over 3. So 1 pi over 3 is about there, 2 pi over 3 is about there, 3 pi over 3 is just pi, and that's there. There's 4 pi over 3, so 5 pi over 3 must be around there. So literally just counting pi's over 3's, pi over 3's around the unit circle here. So here is our angle. Theta is equal to 5 pi over 3. What we're trying to find is the reference angle, which is the shortest distance to the x-axis. So just like we did before, we're going to go measure too far around. So we're trying to find this distance here. So we'll start traveling around and around, and we hit our angle, but then we're going to travel the rest of the distance to the x-axis, the horizontal axis. So that was a distance of 2 pi that I just traveled there. And I want to subtract off just the distance to where we're going here, which was a distance of, oh, I didn't mean to write degrees on that, just 2 pi. And I want to subtract off the distance that I just traveled, which was 5 pi over 3. And this should give us what is left over here. So the full green goes all the way around. I subtract off the pink, and what's just left is this blue here. So if I get a common denominator, I could write this as 6 pi over 3 minus 5 pi over 3, and this just gives us pi over 3, which I don't think was too hard to imagine that this reference angle was pi over 3, because if you add that to where we were, which was 5 pi over 3, you complete the revolution. So we're just using that logic in reverse there. So here is theta prime. It is pi over 3. Now, getting these reference angles can be a nice way to evaluate any angle on here in a quick way. You don't have to memorize so much if memorizing is the way that you're going about this. So before we do that, I want to talk about the signs on sine, cosine, and tangent based on the quadrant that things are living in here. So let's just take a look one at a time here. We'll start over here in quadrant 1. And let's just think that in quadrant 1, the cosine value, these are all the x values here, these are all positive numbers. So the cosine of theta in quadrant 1 is always going to be positive. We get cosine theta is bigger than 0, that means that the cosine is positive. And if I look in the sine direction, well, all of these are positive as well in quadrant 1. So anything that lives over here is going to be mapped to a positive number and a positive number. That's the idea here. So we know that sine of theta is also positive. If I want to take a look at tangent, we're just going to go through the main 3 here. But tangent of theta, well, tangent is just the ratio of sine and cosine, and that's going to be a positive over a positive, which is also positive. So what we see here is that all 3 of our main trig functions are all positive in this first quadrant here. All right, let's take a look at quadrant 2. So in Q2, if we take a look at the cosine, so that's everything that lives on the x-axis, or that corresponds to the x-axis here. Well, everything here is negative. So here we would see that the cosine of some theta that terminates in the second quadrant, keep writing equals, but this is going to be less than 0. All of these cosine values are negative. They're less than 0. But all the sine values are still positive. We're still kind of in this upper half here. So we get that the sine of theta is still positive. And if I wanted to look at the tangent, which is just the ratio of the sine and the cosine, we're going to have a positive value over a negative value, which means that tangent is also negative. So here we see that only the sine is positive. All right, let's move on to quadrant 3. So again, all of these x values are still negative, just like they were last time. So we see in quadrant 3, right in Q3, that the cosine of theta is still always negative. But now we see that we've moved to the bottom half of the circle here, that all of our sine values are still, or are now also negative. So we have sine of theta also being less than 0. If we wanted to talk about the tangent, Well, remember that the tangent is the ratio of the sine and the cosine. Here we have a negative over a negative, which is positive. So here the tangent is actually positive since we're taking the ratio of two negative values. So here we can say the tangent is positive. And then if we take a look at the fourth quadrant here, so here's Q4. We take a look at the cosine. Well, the cosine's back to being positive. All of these x values are positive over here. So the cosine of theta terminating in the fourth quadrant is going to be positive. And the sine values will continue to be negative. So we have sine of theta being less than 0. And if we wanted to take a look at the tangent of theta, we're going to have a negative number with a ratio to a positive number, which means that this is also negative. Tangent is also negative. So that says that the cosine in quadrant 4 is the only one that is positive. So this is the relationship that we are trying to notice and that we can use for reference angles. We know that everything in the first quadrant is always positive. Sine, cosine, tangent, always positive in the first quadrant. If we're in the second quadrant, it's only the sine that's going to be positive. Everything else will be negative. If we're in the third quadrant, it is only the tangent value that will be positive. All other trig functions will be negative there. Well, as for these three. Once we look at the other three, we'll see that there are some corresponding relationships. But for quadrant 4 of these three, it is only the cosine that is positive and the other two are negative. So there's some mnemonic devices to try and remember what is what here. The most, or at least the one that I'm going to go with is a smart trig class. So there's different ones that people use, but A corresponds to all, smart corresponds to sine, trig corresponds to tangent, and class corresponds to cosine. So just kind of traveling around from the first quadrant to the fourth quadrant, all smart, or A smart trig class. So there's some other ones. The one that I usually think of is all students take calculus, which is maybe more popular, but it's not a calculus class, and maybe some of you aren't going on to take calculus, so maybe not the best mnemonic here. But here we will use a smart trig class to just get all of the values as we travel around the unit circle here. Okay, so now we will use some reference angles to compute cosine of 150 degrees and the sine of 150 degrees. So what we're going to do here first is just sketch in this angle. So I'm thinking about traveling around here. That's going to be 90 degrees. If I went all the way, that'd be 150. I'm sorry, 180. So there's 90. If I went all the way around, that'd be 180. So if I backtracked 30 degrees, this should get me to 150. So this is 150 degrees. Different ways you could think about mapping there, but that's the way that I was thinking about it this time. So what we're going to do now is find our reference angle, theta prime, which I already said out loud what it is. It's got to be 30 degrees, right? Because I literally went 180. I subtracted off the 150 that we traveled, and we would get that this is 30 degrees. So we're going to use things that we know about cosine of 30 degrees. And at this point, maybe it's not in the forefront of your brain yet, but at some point you will know that the cosine of 30 degrees is always the square root of 3 over 2. And we're going to use this in conjunction with the fact that we are in quadrant 2, where the cosine is always negative. So remember, a smart trig class. So only the sine is positive in the second quadrant, which means that the cosine of 150 degrees is going to be the same, absolute value, but we're going to make it negative, square root of 3 over 2. So similar, like I said, absolute value. If you take the absolute value of each, we get the square root of 3 over 2. But here, the cosine is negative, so we need to make a negative value here. So I could even tell you what this point is now. This is going to be the negative square root of 3. And now we need to figure out what the sine value is. So we'll do a similar thing here, where we know that the sine of 30 degrees is 1/2. Whether you know that off the top of your head right now or not, it will be something you know soon. And we want to use that in conjunction with the fact that we are in quadrant 2, where the sine value is always positive. So we can put these together to know that the sine of 150 degrees is positive 1/2. It's going to be the same absolute value as the sine of 30, and then we can use the fact that we are in the second quadrant to know that it's positive. So we have got 1/2 there. So there we go. We have got the sine and the cosine of 150 degrees. We can make sure that this is looking right, and this is the way that I usually actually find these values, is that if I wanted the cosine, I could think about dropping this down to the x-axis here, always to the x-axis, and thinking, does this look like it's closer to 1/2, or does this look like it's closer to the square root of 3 over 2? And that sure looks like it's closer to the square root of 3 over 2 because 1/2 is over here. So that tells me that the cosine must be the square root of 3 over 2. And if I think about mapping this back to the y-axis, which tells us something about the sine, that sure looks closer to 1/2 to me than it does the square root of 3 over 2, which is way up here. So this is just another way that you can quickly get these sines and cosines and just think about which quadrant that you're living in. I think that quadrant thing is the most helpful thing here, but using this reference angle, getting it in there, mapping it back to where it lives on the x and the y axis can also be another way to get that. And you'll see me maybe use that technique more often than this kind of more formal approach of using reference angles. So I think we have one more example here. So here we want to find the cosine of 5 pi over 4 and the sine of 5 pi over 4. So we're going to do the same thing. We're going to sketch in the angle, and then we'll find a reference angle, and then we'll think about what quadrant we're in. So if I'm thinking about traveling pi over 4, here's 1 pi over 4, here's 2 pi over 4, here's 3 pi over 4, here's 4 pi over 4, which is just pi, so that makes sense that I'm halfway over. And then there's 5 pi over 4. So just counting pi's over 4 until I get there. So this is going to give us the angle 5 pi over 4. And what we're going to do is look at the reference angle here, which we traveled past 180, 45 more degrees, or we traveled past pi, another pi over 4 degrees. So our reference angle here is going to be pi over 4. We know that the cosine of pi over 4 is equal to the square root of 2 over 2. We also know that the sine of pi over 4 is equal to the square root of 2 over 2. And now we'll use the fact that we are in quadrant 3. And in quadrant 3, the cosine is always, let me draw that a little bit better, the cosine is always negative. So over here, everything about a smart trig class, that tells us that only the tangent is positive over here. So putting these together tells me that the cosine of 5 pi over 4 must be negative square root of 2 over 2. So if I wanted to write that in over here, I've got negative square root of 2 over 2. And again, quadrant 3 tells us that the sine of theta is always negative because it's not the tangent. So putting these together here, we get that the sine of 5 pi over 4 is the negative square root of 2 over 2. So negative square root of 2 over 2. So there we go. We've got the cosine and the sine by just using these reference angles here. So you'll see the same kind of looking values of these square root of 2 over 2, 1/2 square root of 3 over 3, but just with different signs on them depending on where we're living. So that should give us the full unit circle here. So here is everything that has been filled in. We can see that, just like we saw, the square root of 3 over 2 and 1/2 being the point associated with pi over 6. And you can think about mapping things back here. This value here sure looks a lot closer to 3 pi over 2 than it does to 1/2. And this value over here, the y value, sure looks a lot closer to 1/2 than it does 3 pi over 2. I'm sorry, square root of 3 over 2, not 3 pi over 2. So this is something that I encourage you to spend a lot of time with and try and fill out as much as you can. If you are in one of my classes, then we have this posted in our learning page. on Canvas so that you can go download this and fill things in. But you can find them anywhere on the internet. In fact, the one I have, I just Googled blank unit circle, and you can go fill these in and practice. The sooner that you have this thing more or less just ingrained into your brain, it'll make the rest of the class and all of your future classes, pre-calculus and calculus, a lot easier, because you'll have these common values that you'll see a lot kind of already put into your brain. So I encourage you to do that and get some practice filling this out. The sooner that you are familiar with it, the easier time I think you will have going forward. So with that being said, it is time to go practice and put all this new information to good use. So good luck with the homework. If you have any questions, please let me know, and I'll see you in our next video.